Welcome back, everybody. This week, we begin with Ruth Charney, who's going to give the second lecture in the on the class.
Okay, so my lecture today is on geometric approaches to Artin groups. So a lot of you, I'm sure, were in my talk on what day was it? Wednesday, where I introduced and gave a big overview of Artin groups. So I'm going to review at the beginning of this talk. I'm going to quickly review basic definitions and notation, etc. Just to remind you, and for those of you who weren't there, and then I'm going to focus more on what we have learned using geometry about these groups. There's been a huge amount of activity in this area recently, and I have to say it was a real challenge deciding what to talk about here. There were just too many things, and I don't have 3 hours to talk about them. So apologies to if I don't mention your work. I'm trying to sort of focus on certain areas and be able to really talk about how we use some of this geometry. Okay, so let's get started. Geometric approaches to Artin groups. So what's an Artin group? It's a group given by a presentation of a certain form. We have finitely many generators, and we have relations of a certain type. So for any two generators, Si and Sj, we specify an integer Mij, or it can be infinity. And if it's not infinity, we write down a relation, an alternating product of length Mij equals the other alternating product of length Mij. If it is infinity, there's no relation. Okay, no relation. Okay, so usually rather than write out the presentation, we just encode all this information into a labeled graph, which I'll call gamma. The vertices of gamma are labeled by the generators S1 to Sn, and we put an edge if Mij is not infinity, and we label that edge with Mij, so we know what the relation is. So then what we tend to do is just draw the graph gamma, and then we call the corresponding Artin group A gamma. Okay. All right, so we could also, as I discussed in more detail in my previous lecture, the Artin groups are very closely related to Coxeter groups. Namely, if we simply add a single relation, if we take this, if we take this presentation here, and we add just this single relation to that presentation, then what we get is a Coxeter group. By the way, it looks that second, I probably shouldn't have written it that way. That second relation, that SI-SJ, the Mij equals 1, is actually equivalent to that alternating product once SI equals SI inverse. Once SI equals SI inverse, you can multiply by the inverse of the thing on the right, and the relation turns into this one that we're used to for Coxeter groups. Okay, so for every gamma, we have a Coxeter group, and for every gamma, we have an Artin group, and they're related. All right. Let's just look at two quick examples. The first one is the one I talked about in the last talk. A classical example of Artin groups are braid groups. And here's the presentation, the first picture, that's the gamma I've drawn there. All right, so given this gamma, we have 3 generators, and the first and last commute, and the other 2 satisfy what's called this braid relation, length 3 relation. All right, and that's just turns out to be the braid group on four strands, where Si is cross the ith strand over the I plus first strand. Okay, so as I said, I talked about that in more detail before, but if we add the SI squared relation and turn it into a Coxeter group, what we get is just a symmetric group on 4 letters. Okay, so this is a classical example and a case where W gamma is a finite group. We also have, and we're going to be more interested in this talk, on the case where W gamma isn't a finite group. Let's look at the second example. Okay, so what is this? I call the generators A, B, C, D instead of SI. What do we have here? All right, well, let's see. Notice that I'm not going to write out the whole presentation, but let's just think about it. Notice that A and C both commute with B and D, right? That those twos mean commuting relations. AB equal BA. Yes, that's what a 2 does for you. Okay, so what we have is actually a direct product. We could take AC, and it's a direct product with BD. Whatever the subgroup generated by AC and BD are. We have these 2 subgroups, right? And they commute with each other. Yeah. Okay. What is the subgroup generated by A and C? Well, there's no edge. That means Mij is infinity, which means no relation, which means they generate a free group. Okay. They generate a free group. So this guy is actually a free group generated by A and C, direct product, a free group generated by B and D. All right. This is, by the way, an example of something called a right-angled Artin group. Right-angled means you're only allowed twos and infinities and nothing else. Okay, so this is one example. All right, what's the Coxeter group? Well, this isn't terribly fascinating. You just make all the everything length 2, so it now becomes Z mod 2 cross star a free product on Z mod 2s cross another free product on Z mod 2s. So those just turn into order 2. Okay. All right. So that's 2 examples. All right. But there are two important things to keep in mind here is that this Z mod 2 star Z mod 2 is virtually Z. I mean, this Coxeter group is infinite, and an important point about this is that an important thing that's sparked different kinds of research is that we could divide Artin groups into 2 classes, namely the Coxeter groups are sometimes finite and sometimes infinite. The Artin groups are always infinite, but it matters whether their corresponding Coxeter groups are finite or infinite. So we have names for this. If the Coxeter group is finite, we call the Artin group, we say, is finite type, or some people prefer to call it spherical type. I'm going to call it finite type today just because it's a reminder of what we're talking about. It just means that the Coxeter group is finite. And in this case, it's infinite type. Okay, so we have these 2 big buckets of Artin groups, finite type and infinite type. So it turns out that the finite type Artin groups are actually well understood. Yes, there are still a few open questions, but we know an awful lot about finite type Artin groups. We have really nice solutions to the word problems. They're bi-automatic. We know all kinds of stuff, nice stuff about finite type Artin groups. Why? Well, it's because we have this really nice combinatorial structure called a Garside structure. All right. I'm not going to talk about that today, but it's a more combinatorial, not geometric approach. Okay. And recently, this idea of a Garside structure has been generalized slightly. So, for example, there's some amazing recent work by Paolini and Salvetti where they generalized. They found a sort of Garside structure for Euclidean type Artin groups, meaning the ones whose Coxeter groups are Euclidean, and we're able to use that to answer a lot of questions about those groups. So there's been some small generalizations of this Garside structure, but for most infinite type Artin groups, we do not have anything like a Garside structure. We don't have solutions to the word problem. We don't have anything to work with, very little to work with to understand these groups. All right. Okay. So most infinite type groups have no such structure and are largely mysterious. Okay, but that makes them interesting, right? If they're mysterious, they're interesting. Lots of open questions. Okay, so recently, well, starting actually, some of it goes back to some work of myself and Mike Davis, which I'll be talking about, goes back to the 1990s, but then kind of nothing was happening for quite a long time. But recently, there's been an explosion of activity in this area using geometric methods, some of the things we've been hearing about all week this week to help us understand these groups. And so my goal today, oh, interesting. It doesn't like that. It's not going to let me do this, huh? Now, how do I change color? Why isn't it letting me do this? There. Right. Okay. So, yeah, my goal today. All right. So, so there's a ton of different, as I said, there's a ton of different work that's been done in this area using all kinds of different geometric constructions, showing that they have some nice geometry, whether it's systolic or cat zero or injective or whatever, and then using that to get some new information. I'm afraid I can't tell you about all of them. So I decided to focus on a collection of objects that are built out of parabolic subgroups and use the nature of parabolic subgroups to help us understand. So I'm going to focus on a kind of a class of spaces that have been used. So let's talk about what parabolic subgroups are. All right. So so I have my defining graph gamma, and I take some delta to be a subgraph. When I say the word subgraph, I will always mean a full subgraph, which means if I take two vertices that were connected in gamma, I connect them also in delta. I have to connect them in delta and keep the same label. It's just a subgraph that generated by some subset of vertices. Okay, yeah, all right. So I may not always say the word full, but I always mean full. Okay, so it turns out. It's a non-trivial theorem by van der Leck back in the 80s, that there's an obvious map from the Artin group generated by this subgraph delta to the Artin group generated by gamma. I mean, you just take the generators to the corresponding generators. It's not entirely obvious that this is injective on the whole group, but it turns out it is, and that was a theorem of van der Leck. And we call the image of this group, which we'll also call a delta, it's the same thing. And we call the image a standard parabolic subgroup, and then a parabolic subgroup is any conjugate of a standard parabolic subgroup. Okay, so they're just smaller Artin groups sitting inside these big Artin groups. It turns out they just as a comment, this shows up in some of the proofs. I won't talk about it much here, but it turns out that they sit inside there really nicely. They're not only injective, but they sit inside there geodesically, which means if I have any geodesic between 2 points in any word that represents an element in a delta, it must live entirely in delta. It can't involve any other generators. There's no way to get any geodesic word. Any geodesic between, so everybody knows what, so you have, I'll just draw it. You have something like this, and you have something sitting inside of it. And even if geodesics in here in the smaller thing go to geodesics in the bigger, that doesn't necessarily imply that there aren't other geodesics that connect this. What this is saying is, no, there aren't any other geodesics. All the geodesics live inside this sub thing. Okay, all right. So they sit inside there really nicely, and that, by the way, is known for every parabolic of every delta. No restrictions on the at all here. So that's kind of nice. So that helps, sort of reduce to smaller subgroups. All right. So I want to tell you about a bunch of geometric objects we have built using special subgroups or parabolic subgroups. All right, special parabolics or standard parabolics or parabolics. Okay. So first, let's consider the set. Instead of doing conjugates of these A deltas now, I just want to take cosets. All right, so I want to take an A delta and left multiply it by an element of my group and move it around. Okay, so just cosets is a set of objects I want to look at. All right, this set of cosets is a partially ordered set because one coset can sit inside another. So I order them just by, if this coset sits inside that coset, then I say this is less than that. Okay, just a standard partial ordering. Well, anytime you have a partially ordered set, you can associate to it what's called the geometric realization of the partially ordered set. So how do we make a geometric realization of a partially ordered set? Well, we start with, it's a simplicial complex. All right, I'm going to build you a simplicial complex. And its vertices are exactly the elements of the partially ordered set. So in our case, every vertex is labeled by a coset. Every vertex corresponds to a coset, yes? All right. And I connect two of these by an edge precisely when one is contained in the other, right? This is partially ordered. So you can have two cosets where neither one is contained in the other. So, but we only connect them if one of them is contained in the other. All right. And then we just fill in simplices wherever we can. We complete this by whenever we see what's called the clique, which is a set of vertices, all of which are connected by edges, we just fill it in with the simplex. And that's the geometric realization. Yeah.
Do you have all of gamma also?
I'm about to get to that. At the moment, yeah, good question. At the moment, I have allowed all of gamma, haven't I? So we'll talk about that in a second here. So I built this complex. All right, I built this simplicial complex, standard construction. And I noticed that in my group, A gamma acts by left multiplication on this, namely given any coset, if I take an element of you know, say A in A gamma, I can left multiply and G A delta will go to AG A delta. Yeah. It just left multiplication. That clearly preserves inclusions, and so it induces an action on this simplicial complex. Okay, all right. So that's great. So now I have a nice simplicial complex, and I have an action. So let's look at how well behaved is this action. All right. It's not hard to show that it's co-compact. Okay, that's a little exercise. What about proper? All right, so in order for in geometric group theory, proper actions that are co-compact and proper are the best. That's what we would really like. But so this one's co-compact. Is it proper? Well, what's the stabilizer? What are the elements in A delta which fix? So if I do this little operation, when does this equal this? When is the left? When does this stabilize? When does it not move? Well, it doesn't move precisely. So, okay, what's the stabilizer of what did I call it here? G A delta. All right, well, I claim it's precisely the parabolic subgroup. Yes, everybody see that? If I take an element in this parabolic subgroup and I left multiply by this, I get another element of this. Yeah. Okay, so the stabilizers, so I didn't build the complex out of parabolics, but the parabolics show up as stabilizer. And these are definitely not finite. So the action is not proper. It's absolutely not proper, but it still turns out to be really useful, right? It still turns out to be useful. Well, sometimes it turns out to be useful. Let's be careful. If I allow, so there was this question, do I allow delta to equal gamma? All right. Well, I did allow it so far. All right. So what's the state? So that means if I do allow it, what's the stabilizer? Well, now there's there's only one coset, but now there's a point labeled this. And the stabilizer of that is everything. That's not, it turns out, actions where some point is fixed by the entire group don't usually tell you much. This is it's like there's a cone point. That contains everything. I've coned off all the interesting stuff, and this is fixed by the group. And so allowing for that element is not a good idea. In special cases, I will allow for it, which is why I put it in here. But the answer is that's bad. All right, so this is bad news. Okay, so what are we going to do? Yeah, it has a fixed point. All right, so what are we going to do? We're going to look at some restrictions of this. We're not going to use the entire complex. We're going to look at certain subcomplexes sitting inside this thing. So I'm going to restrict which deltas I allow. All right, well, the easiest restriction, the first and obvious restriction, is just throw out the delta equal gamma, just allow everything except the full group. All right, that turns out to be an interest. So here, I'm going to describe for you now 3 complexes, all of whom, they're all subcomplexes of what I just introduced, this geometric realization. And they've all been important in understanding Artin groups. We've used all of them. So the first one is what's called the Artin complex. And the Artin complex is just the complex I described, but we throw out that bad vertex and everything connected to that bad vertex. All right, we throw out all the simplices that contain that top-notch thing, which means, okay, so here we are. So this is our condition here. Yeah, just that it's proper. Yeah, other than that, everything's the same. All right. Turns out that's a nice complex called the Artin complex. All right, another complex that has been used a lot is what's called the clique complex. In the clique complex, we only allow subgraphs of gamma, which are themselves cliques. So no infinity, a set of vertices where no two are joined by infinity, no two are Mij is equal to infinity. All right. So we only allow those. All right. It turns out this also isn't useful if gamma itself is a clique, but it's useful in most other cases. All right. And so that's called that the clique cube complex. And finally, there's another one known as the Deligne complex, because it's a sort of a variation on something Deligne originally defined for finite type Artin groups, but we're going to be interested in it for the infinite type case. And that one, we only allow subgraphs which generate a finite type Artin group. Okay, so we have this big graph. Remember, finite type has to do with the Coxer group, whether it's finite or infinite. We have this big graph, and let's assume that the Coxer group for the whole graph is infinite. All right, but if we were to restrict to, say, a single edge, maybe if you have two generators and an Mij not equal to infinity, that the Coxer group that generates this dihedral Coxer group, which is definitely finite. I mean, every edge generates a finite, and often there are bigger pieces that generate finite subgroups of the full Artin group, right? So we can have a lot of subgraphs which are nice, which have this finite property. All right, where the Coxer group is finite or the Artin group is finite type. So that's the Deligne complex, is we restrict to those. All right, so we have these three subcomplexes, and what I'd like to sort of tell you about now is what we've been doing with them, some of the things we've been working on. So what's been going on, well, for a while, but a lot of new work recently, is to show that is to work with one of these three spaces and show that they we can put some really nice metrics on them, and then use the metric properties to then get theorems to learn about the Artin groups. Okay, all right. So that's let's look at this. All right, let's start with the Deligne complex. That was actually the first one. Any questions so far? All right, so we have these three complexes. They're all made up. The vertices are always cosets, and the stabilizers are always parabolics. It's just a question of which cosets we allow. Yeah. All right. So we're going to start with the Deligne complex. So that's this one here. All right, that was actually the first one that was introduced and used. Mike Davis and I introduced this in the 1990s. As I said, it's a variation on something Deligne introduced earlier to study finite type ones, but we were the first ones to look at the infinite type case. So this complex is tremendously useful for studying Artin groups, it turns out. Okay, so what do we know about it? Well, it turns out that it's homotopy equivalent to a universal cover of some hyperplane complement I talked about in the last talk, and I'm not going to talk about again here. The important thing is that if you could show it was contractible, then you would know that something called the K-pi1 conjecture holds, which is that this certain space, this certain hyperplane complement, is a K-pi1 space. Well, I don't want to go into that here. So instead, let me tell you another version of the K-pi1 conjecture, which I think will be more meaningful for you. There is a nice, beautiful, finite cell complex called the Salvetti complex, which just has one cell for each of the finite type pieces, for each of those finite type pieces. And we know exactly what it is. We know exactly what the cells are. We know exactly its dimension. We know a lot about it. And it turns out that if the K-pi1 conjecture holds, if this hyperplane complement is a K-pi1 space, so is this nice finite Salvetti complex. Okay, so for the purpose of this talk is that if we can show that D gamma is contractible, we get this really nice concrete K-pi1 space, and using that we can then compute homology groups. We get that it has A gamma has finite cohomological dimension. If it has finite cohomological dimension, it can't have any torsion. That's one of the open questions. Do these groups have torsion? You can't. Something with torsion can't have a finite K pi 1 space. And it turns out there's a lot of other questions about Artin groups that don't follow immediately from d gamma being contractible, but usually once we can show this, we can deduce a lot of other stuff. Okay, so this has been really powerful when we can show d gamma's contractible. All right, we've got all kinds of useful information. Okay, so how do we show d gamma's contractible? Well, we've got all these geometric techniques right now for showing things are contractible. My favorite is show it has a cat zero metric. Yes, if something has a cat zero metric, then it's automatically contractible. Yeah, because geodesics are unique and you just can contract things down to any, pick a base point and contract along these geodesics down to. Okay, so let's try and see. So let's ask whether it's cat zero. How many of you have tried to prove something's cat zero? Yeah, okay, very good. Well, if it's a cube complex, usually it's straightforward. It either is or it's not. If you give it a cubical metric, right? I mean, it's a combinatorial property of the links. You have to check this flag complex condition, and it either is true or it isn't true. If it's not cubical, it gets hard to prove something's cat zero. All right, so let's see what we can do. Let's first try cubical metric. Well, I gave you d gamma. I described it as a simplicial complex. All right, but there is a cubical version of it. And to make the cubical version, I want to think of d gamma now as a cube complex, not as a simplicial complex. So how do I do that? Well, I just ignore a bunch of the vertices. So what I do is the following. So let's say I start with, so by the way, in my allowable cosets, so delta is allowed to be empty. I didn't say that, but I can start with a empty set, meaning the trivial group. That's an allowable parabolic subgroup in my, coset in my books. Okay, and then maybe I have another one that's just a single generator, and now I have another one that's just a single generator. All right, well, clearly this is contained in this, so there's an edge, and this is contained in this, so there's an edge. Yeah, and now let's just say that S and T generate a finite type, that there's no infinity. It's not an infinity between them. There's some Mij is not infinity. That means this is also finite type, so that's contained in that. That's contained in that. Oh wait, I see a cube. Now, of course, if I was doing the simplicial complex, I would also connect these by an edge. Yes. I want to just forget those edges. I want to only put in the edges, only keep the edges where I increase the size of my special subgroup by a single generator. All right. I just throw away the other edges. I mean, they're there. I'm just going to ignore them. All right. Well, if you do that, it turns out you have a cubical structure on your it's the same space. I'm just instead of viewing this as two simplices, I'm viewing it as a single cube. Okay. So just keep the edges that change the size of the of delta by a single generator. Okay. All right. So there's my cube complex, and now I just have to check: is it cat zero? Is it not cat zero? Well, it turns out you can just do this. This metric is cat zero if and only if the set of I'll remind you what this is. By the way, the labels on this: prop is for proper subgroups, clique is for cliques, right? And FIN is for finite type. Okay, so it turns out that this is if and only if the cliques are the same as the finite type. That is a sub. Whoops, I didn't need to do that. Let's try that again. This equals this. That is a subgraph generates a finite type sub-Artin group, parabolic subgroup, if and only if it's a clique. All right, that the cliques and the finite things are identical. All right, it turns out that's precisely, in fact, the Artin groups for which this is true are called FC type. FC is for flag complex, because this is exactly the condition that gives you the flag condition you need to get cat zero. Okay, so that's not hard to check. It's straightforward. You just check that cat zero is this, and in this case, we then conclude that d gamma. Oops, not script. Using script for something else. We then conclude that d gamma is contractible. It's cat zero, and therefore it's contractible. Okay, yeah. So we have a whole class. It's great. We have a whole bunch of these things which we know are contractible. Yeah. So that's good. That's a good start. But it's not always true. I mean, the clique and the finite can definitely be different from each other. All right. So this only works in some cases. It turns out there's another metric you can put on D gamma, piecewise Euclidean metric, which is conjectured to always for any gamma be cat 0. For those of you who've worked with Coxeter groups, let me just mention that there's a metric due to Musang, a student of Mike Davis, on the what's called the Davis complex, which is known to always be cat 0. And this is kind of a pullback of that metric. We use the same structure on individual cells. We just have a lot more cells. But it turns out, if for the Coxeter group, there's a nice proof that it's always cat 0. We haven't been able to get very far on this conjecture that it's always cat 0 for the Deligne complex. In fact, we only know it in really low dimensional cases. So it's true if the Deligne complex is 2-dimensional, then yes, you can check, and it is indeed cat 0. And we know a few 3-dimensional cases. We know a little bit of other cases, but essentially low dimensional, 2-dimensional, some 3-dimensional, and we can't get past that. We don't know how to go past that. Okay, but it's a possibility. So I put a couple of names here of people who have worked on this and made some progress on this. Okay, there's going to be names appearing, yeah, all along here. Okay, we could also, so that was the cubical metric we were looking at. All right, we could also put look at this as a simplicial complex and ask whether it satisfies one of these other nice conditions like injectivity or systolicity or whatever. And there's been a little bit of progress on that. Thomas has shown that's true for some of the Euclidean type Artin groups. I guess there's a possibility that could be generalized. Okay, so that's it's a new approach to looking at this from a simplicial point of view. Okay, all right. I also want to mention, though I'm not going to explain quite how this works, because we're going to hear about this next week, I think. Yes. Is Nicola here? Yes, there you go. Okay, you're going to talk about this, yes? No? Okay, excellent. So properties of the geometry of the Deligne complex have also been used to study other questions about Artin groups, such as the isomorphism problem. What's the isomorphism problem? Well, it's the question of if you have two graphs and the groups are isomorphic, does that mean that the graphs were actually basically the same graph? I mean, is that the only way to get isomorphic groups, is to start with the same graph? The answer to that, by the way, is no. We know there are cases when it's not true, but when is it? Are there classes for which it is true? Can we control when two different graphs give rise to the same group? So you're going to hear about that next week. So Nicolas and Alex Martin have been working on that. Okay, so let's move on. So that's the Deligne complex. I would love to know that more Deligne complexes are contractible, if anybody has suggestions of how to prove that. So how about the clique cube complex? Well, the clique cube complex, we can do the same thing we did to the Deligne complex and view it as a cube complex instead of simplicial in the exact same way. Just keep the edges that change things by 1, and so there's a cubical structure on that. Guess what? That cubical structure is always cat 0. There's nothing that you check, and just by definition, that one is always cat 0. Okay, wow, we have something to work with that's always cat 0. Well, it turns out to be really useful unless the whole gamma is a clique, in which case, again, we get this cone point and we learn nothing. All right, but what we do have learned from some work of Ellis and Skolberg and then Gödel and Paris, is that when gamma is not a clique, you can reduce, when the whole graph is not just one clique, you can reduce many of the conjectures about A gamma to questions about the clique subgroups. That is, if you knew that something was true for every one of its clique subgroups, you could use this complex to then deduce that it's true for the whole group. All right, so in a sense, it takes many of the conjectures we're trying to prove about gamma and about A gamma, and says we just need to understand what happens when gamma is a clique. That if we could understand that, we'd be done. That's what that's essentially what this construction does for us. All right. Okay, and in general, you know, I'm going to hopefully have, I think I'm going to have time for a quasi little bit of a proof of some of this. Is the general idea that you can use these spaces to reduce questions about the big group to questions about stabilizer subgroup, to smaller groups inside there. And so if you understand how the smaller groups work, then you're in business. Okay, we'll talk more about that later. Okay, so that's basically what this has been, the clique complex has been used for. All right, that brings us to the Artin complex. And the Artin complex, I want to say, is relatively new in the sense that using it, looking at the geometry of it and using that geometry is something that's been quite recent. All right, the Deligne complex has been around for, you know, when did we introduce it, 95 or something? Anyway, the Artin complex, the work on the Artin complex is all new, and I think it's you know, got a lot more potential. People are just now really getting into it and understanding it. So I want to mention some very recent work by Jinying Wang, extending some things and some ideas from Thomas Hatel's work to understand the geometry of this Artin complex for a lot of gammas. All right, so what he's done, and you know, I'll do my best to describe this, but you might want to ask Jinying for more details, is to come up with some combinatorial conditions which can be used to show that X gamma has a nice geometry. And nice geometry in this case means it has in particular, one of the things it means in this case is that it has a convex geodesic bicombing. But that's, you know, almost as good, not quite. Oh, and I said in cat zero case, we had unique geodesics, right? So we could contract by picking a base point and just sliding everything down along the base point. Well, now we don't have unique geodesics, but we have a choice of path between any 2 points. We have a preferred choice of path, and these paths behave nicely with respect to each other. So again, we can just contract along these paths and get that our space is contractible. Okay. Okay, it turns out it takes the arguments are slightly different than in the Deligne complex, but it turns out once you show this, you can also deduce the K-pi1 conjecture for if you can show this thing is contractible. Okay, so what I'm really excited about, I don't totally understand this paper yet because it just came out 2 weeks ago and I haven't quite absorbed it. But one of the things that excites me about it is it's not just about low dimensions. You know, it's not all in 2 dimensions or 3 dimensions. We're finally getting some progress on higher dimensional examples and the potential to do even more with these kinds of arguments. So I think this is, you know, an exciting new direction that we might be able to go in. There are some other applications of the Artin complex, and I'm going to get to those a little later. I don't want to mention them yet because I want to first introduce something called the complex of parabolic subgroups. Actually, before I do that, any questions? All right. Okay, so yeah. X gamma, that's good. Is that true? Is it known to be simply connected in general? I think it's always. Yeah. Right. I don't know. Okay. Okay. So good. Yeah. So those are so all these 3 complexes have been really useful in helping us learn some stuff about.
So this is all proof that it's
for this certain class that are in, I can't describe the details of it. It gets certain conditions, certain combinatorial conditions have to be satisfied by the graph. You know, if the graph satisfies certain is of a certain type, but the good news is those include a lot of higher dimensional cases. It's not just two-dimensional. It's like all kinds of higher dimensional cases. Okay, so let's move on. There's one more complex that I want to talk about that also involves parabolic subgroups, but in a rather different way. All right. Okay, so I'm just going to call it the complex of parabolic subgroups. Namely, instead of my vertices being cosets, I want my vertices to be actual parabolic subgroups. All right. So let me introduce this by starting with where this idea comes from, by starting with braid groups, which, as I said, are a classical example of Artin groups, but they're also an example of mapping class groups. All right. So there's a whole theory of mapping class groups of surfaces, and braid groups are a special case of this. They're the mapping class group of a punctured disk. So the n-strand braid group, if you take a disk and you put n holes in it, then it turns out that the mapping class group, that's the group of homeomorphisms of this surface up to isotopy, that this mapping class group turns out to be the braid group. All right. Well, there's a whole, huge amount of structure and theory about mapping class groups. And one of the most useful objects that's played a big role in the study of mapping class groups is something called the curve complex. All right, the curve complex is a simplicial complex, or the curve graph, if you want. It made up whose vertices are simple closed curves in your surface, and two vertices are connected by an edge if those simple closed curves don't intersect each other, if they're disjoint from each other. All right, so they could be in two separate places, or one could be inside the other, but it can't touch it. They can't touch each other. Okay, so so this is called the the curve the curve graph, and then if you want to fill in the cliques, then it's a curve complex. It doesn't matter. It's really only the graph I care about. Okay, so an interesting question is, if we think of the braid group instead of as a mapping class group, if we think of this as an Artin group, can we describe what this curve complex is purely in terms of the Artin group structure, purely algebraically in terms of this group structure? And it turns out that you can show that simple closed curves correspond to parabolic subgroups. So, for example, if I were to, let's see, if I were to circle this, that's a simple closed curve, all right? And what I'm going to allow, the parabolic subgroup is going to be mapping class stuff that takes place entirely inside this, where I don't move anything. It's the identity outside that. So, for example, I can interchange the first two elements, punctures. I can interchange the second two punctures. This is going to be the parabolic subgroup generated by S1 and S2, by the first two generators. All right, and one can show, it turns out, that there's a one-to-one correspondence between simple closed curves and parabolic subgroups. All right. Okay. Yeah. So I told you what the curve complex is. I'm using script CS is simplicial complex with vertices, simple closed curves, pairs of disjoint curves, and oh yeah, I forgot to say one more thing. Why is this curve complex so important in the mapping class group situation? Well, one reason is that it was proved by Mazur and Minsky that the curve complex is hyperbolic. So you get an action in the mapping class group on a hyperbolic space. This has been used as a motivating model for the whole theory of hierarchically hyperbolic groups and spaces. If you've ever seen this, this is this mapping class group action on the curve complex has motivated a lot of recent study in geometric group theory. Okay, so it was interesting to us to think, could we make sense of this for other Artin groups than just the braid group? Okay. Okay, so we've got this correspondence in the braid group case. So how about if we use parabolic subgroups to try to construct something like a curve complex? All right. Okay. So that was the question. Is there an analog of the curve complex for Artin groups using parabolic subgroups? All right. So you have to understand, to do this, you have to understand, I told you what this corresponds, but what does it mean for two simple closed curves to be disjoint? What does that tell us about these parabolic subgroups? When does that, what relation on the parabolic subgroups corresponds to an edge in here, right? So we really have to understand how these things interact. Okay, so this was first done and studied in the case where A gamma is finite type, as the case where I say we usually understand things, by in this paper by Completo, Gebhardt, Gonzalez, Meneses, and Bert Wiest. They gave a really beautiful description of when two parabolics corresponded to disjoint curves. They were able to give a very concrete description in terms of the Garside elements commuting. I mean, it's very, I can't tell you it here, but it's really straight. It's really very, very comprehensible and not difficult to check. Okay. But to do that, and even to construct this complex in a well-defined way, they needed to know some really basic facts about parabolics. And when I first looked at their paper, I was excited that they constructed this thing, and I was mind-boggled that we didn't know these basic facts. I said, we don't know this about parabolics, even for finite type? It turns out there are these basic questions that we didn't even know for finite type. So here are three things that they proved and needed for their construction. All right. The first is that the intersection of two parabolic subgroups is again a parabolic subgroup. Seems right, but so it turned out to be difficult to prove that. The second is that the partial ordering on the set of parabolic subgroups is a lattice, meaning given any two parabolics, there's a unique so ordered by inclusion, there's a unique greatest lower bound and least upper bound. So if you take this set and partially order it, then any two elements have a unique greatest lower bound and least upper bound. Okay, that's what we mean by a lattice in this case. All right, so those behave nicely. And finally, using these properties, one can show that given any element of the group, there's a unique smallest parabolic element containing that element. It's called the parabolic closure of the element. All right. So these are, properties that you think, oh yeah, sure, but they were not easy to prove. All right. Okay. So we know that for finite type, which brings us to our favorite question, which is, do these properties also hold for infinite type? Right. And if so, can we then define some kind of cube complex that is nicely behaved? And of course, ultimately, we want to prove that it's hyperbolic, but I have to say we don't even know that for finite type case yet. So that was way wide open. All right. So even finite type case, but even the construction for infinite type case, not only is the construction of the curve complex interesting, but just these questions about parabolics would be really useful to know, because the parabolics show up in all these other constructions. They show up as stabilizer subgroups and this and that and the other. So it'd be really useful to understand how they interact with each other. All right, so I'm interested in this question. And it turns out, when we can put nice geometries on either the Deligne complex or the Artin complex, we can sometimes answer these questions for infinite type. How do we do it for infinite type? Well, we put a nice geometry on one of these spaces and we try to use that. Okay, and there's been some very nice progress on this question, namely proving. So the question I'm talking about is this, namely, can we prove these properties for other Artin, for infinite type Artin groups? There's been some progress on that by Rose Morris Wright, a former student of mine, Completo, Martin, Vascu, Stein, I didn't pronounce that right. Muller, Paris, Varghese, et cetera. There's been a lot of interesting, there's lots going on in this area. It's a really nice question. So what I would like to do, I didn't know if I'd have time or not, but yes, I think I do, is to give you just a little bit of an idea of how these proofs go. I thought I'd try and actually use the geometry to show something. Okay, so let me just, this won't be a complete proof, but just give you some idea of what kind of arguments go into something like this. Okay, so we're going to work with, I'm going to work with the Artin complex, but there's similar arguments for the Deligne complex. So it turns out, okay, so I'm using the Artin complex. Where are the parabolic subgroups? Well, the parabolic subgroups show up as stabilizers of vertices, right? The vertices themselves are cosets, but the stabilizers of the vertices are parabolic subgroups. Yeah, everybody remember that? Okay. All right. So the X gamma is the Artin complex, which means I allow all proper subgraphs delta in my, any proper subgraph is allowed as one of my, for my vertices. Okay. So let's say I have an X and a Y in here, which means these are two vertices. Oh, yes, they're cosets, but I don't want to name them. I'm just going to call them X and Y. I picked two vertices in here. And I'll call P sub X and P sub Y the stabilizers of those vertices. So those are parabolic subgroups. And conversely, by the way, given any two proper, I might have started with two parabolic subgroups, and I want to show their intersections parabolic. Okay. So given any parabolics, proper parabolics, not the whole group, any parabolics proper, it is a stabilizer of some vertex. And if you write it as G delta G inverse, then it stabilizes G A delta. It's a stabilizer of some vertex. So I can always realize my two parabolics as stabilizers of two vertices. Okay. All right. Well, it turns out if you have a sufficiently nice geometry on X gamma, that you can show that if something fixes two vertices, it has to fix an edge path between them. So let's just take just to explain what's going on here. I'm not going to prove this, but let's just take, like, if it was maybe a cat zero cube column. Let's just say we had it like cat zero. Well, in cat zero, it fixes a geodesic, but a geodesic needn't be an edge path, right? It can cut through simplices, but the nature of the simplices or cubes here, because of how the action works, it never permutes a cube. If it fixes any point in the cube, it fixes the whole cube because it fixes the delta. It doesn't change the delta. It only changes the thing that appears in front of delta. So no element, because of how these are built, no element can fix, as soon as it fixes a point in the cube, it fixes the whole cube, which means if we just look at this path, just take any edge path that stays in the cubes containing this path, and it's fixed. Okay, so we get fixed edge paths between any 2 points like this. All right, so now let's look. Now we want to so P sub X fixes X, P sub Y fixes Y, and I claim that the intersection has to fix an edge path because it fixes both ends, so it fixes an edge path. All right, so here's my edge path. What does an edge path look like? Well, so because it comes from a partially ordered set, as we travel along the path, we're always traveling along an edge is either a downward edge or an upward edge, depending on whether we're making our coset smaller or larger. So I've drawn a path. It goes down for a while, then it goes up for a while, down, up, okay? And I only care about these turning points, all right? So I labeled the turning points, P0, P1, P2. Well, of course, I'm cheating here. What I'm labeling it with is the stabilizer subgroup, not the name of the vertex. I don't care about the name of the vertex. All I care about is what stabilizes it, okay? So I've labeled it with the stabilizer subgroups of those vertices, all right? Okay, so now I'm going to do an induction on the length of this path, all right? Let's say this path just goes from P0 to P1. It's just one, it goes all up or all down. Well, that means either P0 is contained in P1, Pn, that should be, yeah, P1. So where in this n equals 1 case, this is Px and this is Py, right? So it means that one of them is contained in the other. Either it's all down or all up. One is contained in the other, then obviously the intersections are parabolic, nothing to prove. Okay, check. We're good. All right. All right. Let's take the n equals 2 case because you already see some interesting things happen. Let's just look at the case of 2. So I'm going down up or up down, one or the other. All right. Okay. So in the down up case, ooh, I'm almost out of time. That's okay. This is the last thing I'm going to do. What's going on here? Well, it's clear. I'm interested in the intersection of these. By from the picture, it's clear that P1 is contained in the intersection because P1 is contained in P0 and P1, these are upward containments. Yeah, no problem. But I claim that the intersection is contained in P1. Why is that? Well, what we know is that if something fixes, if something's in this in the intersection of P0 and P2, then it fixes those 2 points. And so our whole hypothesis is it fixes the path between them. In particular, it fixes this vertex V. All right. So the intersection fixes V, but the only things that fix V are P1. That is the stabilizer of V. All right. So I claim this is also true because this is the stabilizer of V, and we know that the intersection stabilizes V. Can you see that? Okay. All right, great. So the intersection is a parabolic subgroup. We're done. All right, good. Okay, what about this direction? This direction, what we have, what we have is that P0 and P2 are both actually are both contained in P1, which is itself some kind of parabolic, okay? Well, up to conjugating by G, let's conjugate it by G, we can view these as being contained in a smaller Artin group, in the Artin group for a smaller graph. And so what we need to do is induction on the size of delta. We need to assume we've proved it for smaller Artin groups and then say, well, if it's true in A delta, then the intersection, so assume by induction that the theorem holds, meaning intersections of parabolics are parabolic. That theorem holds for A delta. And then we say, okay, I'm looking at 2 parabolic subgroups of A delta, but I know in A delta intersections of parabolics are parabolic, so I'm done. All right. Okay, so you just reduce it to a case of a smaller. So most of the arguments using the geometry of these things basically take a question and reduce it to something inside a stabilizer, which is a smaller Artin, group. That's the nature. Okay, obviously I only did it for n equals 1, n equals 2. So there's another induction, which then inducts on the length of the path, but that's basically how the arguments work. Okay, all right. So I just wanted to give you a little idea of how these arguments. So the key fact about the geometry was that if you stabilize 2 points, you stabilize an edge path between them. Okay. All right. Okay. So that's basically all I'm going to say. I just want to point out, I've already pointed this out, that none of these actions that I've been talking about today are geometric because they're not proper. You know, we'd love to have geometric actions on some nice spaces. And there are definitely people who are working on those questions. Is it possible, you know, which of these groups are cat zero? Can we build cat zero spaces, heligraphs, systolic complexes on which these act geometrically, you know, have better actions in this? And there has been some interesting work done on that by various people in this room. Stay tuned.
Are they called parabolic subgroups? Why are they called parabolic?
I was wondering that too, but
That's a good question. What's the history? You know, usually that's from sort of representation, more from Corey. Do you know the answer to that one?
I think they have come
Or-
from variables.
Yeah. Oh, because well, yeah, but why are the Coxer group? Oh, because of the Weil groups. I see. Oh, okay, that's right. Yeah, so it starts with the Coxer group. So you have a similar definition for the Coxer group. You know, it's for and there's these for many Coxer groups anyway. There's a strong connection, you know, with representation. There's representations of these things, and now you're in some linear group, and there we have a notion of parabolic, and that's the correspondence by using the correspondence of the Coxer groups inside the linear groups. Yeah, I should know the answer to that. I never really thought about it.
somewhere there was a fixed.
Where does the finite type assumption come into the proof of intersection of parabolics being parabolic?
You mean that we're using the, wait a minute, where does the finite?
Type assumption come in? Wasn't that?
No. So if you're using the Deligne complex, no, so yeah, okay, I'll explain that. So we can only show this, we can only do this argument when we have a nice geometry on our space, whether either X gamma or so when we use D gamma, all right, we have a lot of cases where we have nice geometry on D gamma, but in D gamma, the only parabolic subgroups that show up are parabolics for finite type, for the finite type, the only deltas that were allowed. So there we can only do this argument when our initial P1 and P2, our initial parabolics were stabilizers of vertices in D gamma. And in that case, they have to correspond to finite type subgroups. All right. So we can only do this argument when we have a nice geometry on our space. All right. So we would love to do it. So this thing, getting, that I needed to be able to realize these two parabolics as stabilizers of some vertices, right? And if I'm working in D gamma, the only ones that show up are stabilizers of finite type things. And so if I wanted to use X gamma, because there I didn't have to worry about that, all proper parabolics show up, but we only know that X gamma has these nice geometries in some very special cases. We can only do this in some very special cases, all right? D gamma has nice geometry in a lot of cases, but then we don't get all the parabolics. That's the problem. We get the parabolics, we can only do the parabolics that show up as stabilizers, all right? So X gamma is the space we'd like to use because all of them show up, but we don't have nice geometries on that jet, for enough cases yet. Does that answer the question? Okay.
There was, it seems like there's some kind of pre-production arguments in the end. And that's usually used to prove contractibility. So is there something that fails in that pre-production here?
But these cases will be contractible. So what's the?
Oh, it's in the contractible case.
I think so. I think all the cases where A gamma is known to have these nice geometries are contractible anyway. But we don't get that doesn't tell us about parabolic. I mean, that's an independent question actually. Whether these parabolic. So as I said, we didn't even know this for finite type. We didn't know this for anything. I mean, contractibility of the complex will not answer this question. I guess is yes, they will. Those are okay. That's happened. In a lot of these conjectures, as I said, once you know that D gamma is contractible, it only instantly implies a few of the conjectures, but usually you can derive the rest of them by some other playing around. So they're related in some abstract sense, but there's no direct connection between those two questions. None that I know of, anyway. Yeah.
You said the when they're not proper, are they cylindrical or maybe non-uniform?
Yeah, I mean, there's definitely been work on those questions. Yes, and in some cases we know that to be true. Yeah, so questions about acylindrical hyperbolicity, there's quite a few cases known for that. I decided not to talk about that, but yes, definitely. Various results on that.
Really know how many Artin subgroups, for example, so every Artin subgroup of the Artin is a problem, or
Is what? Or
if every Artin subgroup of Artin is a problem.
well, what do you mean by an Artin subgroup? Oh, something isomorphic to some Artin group? You mean if some subgroups isomorphic?
Yeah, I think he means like a subgroup
Yeah,
that's
not-
also an Artin group.
Right. Oh, whether it's parabolic? No, that's not true. Yeah, it's not true. That's not. Yeah, it's not the case. Yeah. Although, yeah, there is this isomorphism problem showing that, sort of you can see certain types of subgroups inside the, you can detect subgroups of certain types, but they're not all parabolics. No.
So the question, well, if not, we will resume at 11 and let's